Thank you for the introduction. Hello everyone, my name is Hamidreza Tahsiri. I'm a PhD student at the University of Houston, working under the supervision of Dr. Belarbi and Dr. Dawood and Dr. Gencturk. The outline of my presentation is first a quick introduction about the research project that we are working on at the University of Houston. And then I will talk about two separate topics. One, a stress relaxation test, and then about HARPING characteristics of CFRP tendon, and at the end I have the concluding remarks. As you all know, traditional application of steel in bridge construction causes several durability-related issues, such as high maintenance and repair costs, and reduced service life of the structure due to corrosion of steel. One solution for this problem can be replacement of the steel with a more durable material like CFRP composite, which consist of carbon fibers as a reinforcing elements to take care of the applied load, and we have the matrix resin to bind the fibers together and transfer the stresses among the fiber and also protect the fiber from external damages. And some of the benefits of CFRP can be mentioned as high strength and stiffness to weight ratio, high resistance to electrochemical corrosion, and reduced maintenance costs. So the CFRP project that we are working on has two main goals. First, to investigate the application of this material in bridge girders, both pre-tensioning and post-tensioning application. And more importantly, to develop design guidelines in H2 LRFD format. So we conducted several material testing to assess the short and long-term performance of this material. Then we implemented this CFRP material in design and fabrication of full-scale bridge girders with the slab and both pre-tensioning and post-tensioning, as I mentioned. And also we conducted flexural testing under monotonic and fatigue loading. And at the end, by collecting the data from other research studies and based off our results, we end up with the proposed design guidelines to be included in the H2. All the design requirements that we identified and we look into details are presented in this slide. We have the CFRP characteristics, stress limit for CFRP tendons, prestressing losses, flexural design, serviceability limit states, and transfer and development length of CFRP. This table is a summary of two of the design requirements and what is in current H2 for pre-stressing steel and what is going to be changed or modified for CFRP in our guidelines. For instance, regarding stress limit of CFRP tendon, for a straight tendon, we have lower jacking stress limits. As you know, because of creep rupture restrictions in CFRP material and due to brittleness of this material, that we have to maintain enough reserve tensile capacity. So we have to lower the jacking stress limits. And also regarding harping and in deviators, we have some restrictions on the harping angles and deviator sizes that need to be included in our guidelines. And also we look into all the pre-stressing losses, including instantaneous and long-term losses, such as relaxation, concrete creep and shrinkage, temperature effect, friction losses, elastic shortening, and anchorage sets. So on this presentation, I'm only focusing on the two items, harp and drape and relaxation tests. Two types of Prestressing CFRP material were included in our project. 7-wire twisted CFRP cable with 0.6 inch diameter and CFRP bars with 0.5 inch diameter. Some of their material properties are summarized in this table for comparison. So let's talk about the relaxation. Relaxation defines as a time-dependent loss of prestressing force in a tendon under constant strain situation. In general, creep and relaxation mechanism can be explained through theory of viscoelasticity. Several viscoelastic models previously developed to explain the relaxation phenomena. What is common among all these models? We have a linear spring to present the instantaneous behavior, and we have the linear dashpot in the model to present the viscous or long-term behavior. One of the very basic models for presenting the relaxation in the CFRP composite can be Maxwell model, which includes a linear spring and a linear dashpot in series configuration as presented in this figure. By applying the constant strain to the system, the time-dependent stress can be obtained as an exponential function of the time, as presented in this equation and also plotted on the figure. Also, more complicated models also developed by including more elements in the system, but we have to notice that the more complicated the model is, we get the better and more realistic results, but we have to consider a lot of effort to define the material characteristics of each element in the system. However, by experimental studies, relaxation in FRP composite found to be linearly related to logarithmic of the time. As presented in this equation, the constant values A and B can be obtained from experimental result by regression analysis. As a sample, I have the relaxation result of a CFRP cable with respect to logarithmic of the time. As you see, by extrapolation of the best fit line to the experimental result, we can obtain the 1 million hour relaxation, which corresponds to around 100 years, around 2.43%. Another important aspect of the study is to understand the sources of relaxation in a CFRP composite. So we have the main sources of relaxation. First is the matrix relaxation, which is happening in a relatively short period of time after applying the load. And then we have the fiber strengthening, which is due to misalignment in fiber orientation in the composite. After applying the load, due to time, these fibers start to strengthen by flowing through the matrix, and this process causes further loss of load or stress. And we have the wire strengthening in the case of twisted wire cables, and also fiber relaxation by itself, which in the case of carbon fibers is known to be close to zero. And these SEM pictures showing the misalignment in the carbon fibers in two types of CFRP with 0.76 inch and 0.6 inch diameter. Another important factor is to consider the effect of anchorage losses on the total relaxation of the CFRP system. As you know, in post-tension application of CFRP tendon, we have the anchorage at the end of the CFRP as a permanent element. So due to time, by introducing the stresses, the CFRP start to pull out, and this pull out or progressive slippage of the CFRP inside the anchor can be another source of loss in the system. So by reviewing the previous studies, the research gaps identified as limited relaxation test duration. Previously, most of the research is conducted is between 1,000 to 3,000 hours. The effect of length of CFRP on the relaxation losses need to be investigated. The effect of anchorage losses need more attention, and also due to contradictory research results previously, and also due to advancement in CFRP product, we need to do more and new tests and experimental studies to understand the behavior. So in the research program, we have our test specimens, which are CFRP cable or bars with different lengths and all anchored at both ends. We have 15 specimens per type of CFRP. The test parameters are the level of jacking stresses, which are 50, 60, and 70% of design tensile strength. We have the Prestressing CFRP length as another parameter, and also the type of CFRP. The anchorage system that we used are the socket type or bond type anchor, which are threaded steel pipes filled with highly expansive material to generate the expansive pressure uniformly through the length of the anchor to enhance the bond and reduce the slippage and losses. So the production of the anchorage system conducted in 3 steps. First, we placed and fixed the CFRP tendon at the center of the anchorage system, and then after mixing the expansive material with water and pouring the expansive material inside the anchor, we let it cure and set for at least 24 hours to generate enough expansive pressure inside. After preparation of the specimens, we placed the CFRP inside a very stiff hollow structural steel section, or HSS. We lock the specimen at the dead end by using the knot and end plates. And then at the other end, at the jacking side, we have the application of the steel chair, the coupling adapter and threaded rod, and also the hydraulic jack and the load cells. So the pulling is happening by transferring the load through the adapter to the threaded rod, and then we apply the prestressing force. After reaching to desired load level, the anchor at the live end or jacking end gonna be locked, and then we start the process of measurement, which we have load cells and strain gauges to continuously monitor the stress and strain level of the system. Also, we conducted the same process on the very short specimens, the anchorage specimens, including the 2 socket and a small gap between them to be able to fill the expansive material. And the same process also repeated to measure the anchorage losses. Now I would like to talk about the some of the results. Here I have the stress ratios with respect to logarithm of the time for all the specimens at the same length, but with 3 different initial pre-stressing. As you see, for both CFRP cable and bars, we observe the linearity between relaxation and log time, and also higher stress level resulted in higher relaxation as we expected. Also, here we have the result of the specimen with different length, but at the same level of pre-stressing of 60%. And as you can see, for 10 feet, 15, and 20 feet, the results are on top of each other. So we concluded that the length has no effect on the relaxation, or has a minimum effect. So here we are showing how to subtract the anchorage losses from the total loss of the system to obtain the pure relaxation of the CFRP. At the very left graph, we have the relaxation of CFRP cable and bars at 60% initial jacking. And in middle graph is the relaxation obtained from the anchorage or the anchorage losses of the CFRP and cables, again at the same level of pre-stressing, by subtracting the anchorage losses from the losses of the system. We obtain the pure relaxation at the very right figure. We also developed the relaxation equation in Ashto format for the case of post-tensioning by including the anchorage losses as presented in this slide for both CFRP cable and bars. Also, we have the same set of equation for pre-tensioning application by subtracting the anchorage effect. And this figure shows the relaxation of CFRP cable and bar compared to regular steel up to 114 years. The extrapolated relaxation of cables are around 5.4%. However, for the bars, we have lower relaxation of 3.9% in compared to a steel, which is 15%. And after subtraction of the anchorage losses, we got 4.8% for CFRP cable and 2.1% for CFRP bars. The next topic that I would like to talk about is the harping characteristic of CFRP tendon. The main objectives are to understand the tensile flexural behavior of the Prestress and CFRP cables and bars in the harp and deviated configurations, to investigate the feasibility of harping, and to evaluate the reduction of tensile strain and jacking stress limits. So as you know, application of Prestress CFRP in harp configurations has been limited due to lack of knowledge about this topic. So the effective components identified as the deviator size, which is in the case of prestressing with steel is usually 1 or 2 inch. And we have the harping angle, which in the case of pre-tensioning, in pre-tension bridge girders varies between 4 to 12 degrees. And the contact surface material and the type and size of the Prestress CFRP can be other effective components for harping. This slide shows the distribution of stresses in a harp CFRP at the location of deviator. First of all, we have the contact pressure, which indicated with a red color in this figure. This contact pressure will increase by reducing the deviator size and increasing the harping angle or reducing the contact surface, which can lead to premature failure of the CFRP due to weakness of this material in transverse direction. However, in the case of steel, we don't have this concern. Also, due to bending of the CFRP at the deviator location, we have the induced tensile flexural stresses indicated with green color, which can reduce the overall capacity of the tendon. However, again, for a steel, due to ductility and yielding, this won't have any effect. And the current equation, which is mentioned in ACI 440, is not very accurate to calculate the reduction of tensile capacity. As you know, this equation is only function of modulus of elasticity, radius of the tendon, and radius of deviator. And there is no sign of harping angle in this equation. And the assumption behind is that the radius of deviator is the same as the radius of curvature of a harp tendon. However, which is not the case. And by applying the pre-stressing force in different harping angles, it can be changed. So this portion requires more attention. So the research gaps are the lack of knowledge about harping effect, limited analytical and experimental studies, and deficiency of current model in predicting the behavior. The test specimen, again, CFRP cable and bars anchored at the end. We have 36 specimens per CFRP type. The test parameters are the deviator size, deviator material, harping angles varies between 5 to 20 degrees, and the type of CFRP. So the process starts again with production of the anchorage system, which again we have the potted type anchors filled with highly expansive material. In this special case, we have the application of wedge and grip, wedge and sleeve grips to apply the pre-stressing force. The test setup presented in this figure. We have a reaction frame, back-to-back steel channels, and ice steel section at both ends. prestressing CFRP anchored at one end, at the dead end, and on the other side we have the hydraulic jack to apply the prestressing force, and by moving the anchor at the dead end up and down, we can obtain the desired harping angle. So we first studied the 1 inch and 2 inch, which is used for a steel practice, and then we increased the harping deviator up to 20 inch diameter. The preliminary test results were not very satisfactory. First of all, 1 inch and 2 inch deviators in the case of CFRP bars retain the maximum of 31% design tensile capacity, and for CFRP cable was higher, 55%, which is not still enough to be used. And also by increasing the deviator size to 20 inch, we still didn't get enough retention of tensile capacity, and one of the reasons is due to highly concentrated stresses at the location of deviator, which caused premature failure of the CFRP. In the case of CFRP bars, we have the splitting cracks, as you can see here, which end up to failure at a very small load. And in the case of CFRP bar cables, we have the local failure of the wires. So our preliminary conclusion was that 1 inch and 2 inch diameter deviators that are used for steel prestressing is not suitable to be used for CFRP. And also we recommended to not use the CFRP bars in bridge girders due to the range of harping angle that is required there. So with the idea of increasing the contact surface and reducing the contact pressure, we developed two deviators. One of them it has a 6-inch straight portion and 20-inch diameter of the curve, and the other one had the 10-inch straight portion and 40-inch diameter of the gear. And the result this time has improved a lot. So by under 20-degree harping angle with 20-inch diameter deviator, we retain as high as 94% of design tensile capacity of the CFRP cable. And by using the 40-inch diameter, we retain 100% of design tensile capacity of the CFRP cables. Here we have the comparison between 20-inch and 40-inch deviators. By using the 40-inch deviators, we retain 100% in all harping angles. And here is another representation of the results. And for CFRP bars, also we conducted these tests with the new developed harping devices. By having the 5 and 10 degree harping angle, we reach up to 76 and 80% of design tensile capacity, which was a big improvement, and we were able to avoid the premature failure of CFRP bars. But under higher harping angle of harping angle of 15 degree, we still experienced the premature failure and significant reduction in the tensile capacity. So the concluding remarks are the linear relationship between stress relaxation and logarithm of the time. Stress relaxation is invariant of the length of the specimen, and the equations were developed for both pre-tension and post-tension application. And relaxation of CFRP system are less than half of the value for steel. And regarding harping test, I'll talk about the effect of large harping angles and deviator sizes, the premature failure due to high contact pressure that by using the new harping devices that we developed, but it required more attention to be able to be adopted by the industry and to be practical, is still yet to achieve. And application of new harping devices with large contact surface and higher retention of tensile capacity for CFRP cable than CFRP bars in all cases. And at the end, I would like to thank to all of you for your attention, and this was the end of my presentation.
Any questions for our speaker? All right, got one. 444R, based on what you've learned in this study, what recommendations would you make for the 444R?
Yeah, actually, regarding the relaxation, we don't have any specific equation in 440R. Actually, there are some. There have been several studies, but they don't have any equation to obtain the instantaneous relaxation of the system. So this is one of the missing portion. And regarding the HARPING, as I mentioned, the equation is not very. This is based on previous studies conducted in 2000, and there are some other analytical work that conducted after that, but this equation did not change after that time. So this stuff based off my scope of my presentation, but also regarding other, for example, the resistant factors, the phi factors that we are working on by doing reliability analysis. The proposed whatever is right now in the current ACI 440 is not very efficient. And another aspects that I can mention is the equations for flexural design, and the especially for the concrete strength when we have the alpha and beta equation. So in what is happening is, in the case of FRP, we may not have the crushing of the concrete as the failure mode. So the equation of alpha beta is basically by considering the ultimate strain of the concrete at the end, 0.85, and the equation needs to be updated. So these are all the items that we work on in our project to be included in the HDO. Thank you.
No, it's very, very good presentation, but only small comment. I think the result that you got applies specifically for the material that you tested, because I saw an example for the CFRP bars, that some interlaminar shear failure.
Yes.
And this is really interface fiber matrix interface problem.
Yes.
And maybe you'll discover maybe the bar that we tested are made with carbon fibers and maybe vinyl ester. Which is not really compatible, because most of the carbon fibers are compatible with epoxy resin. So we'll test maybe some CFRP bars made with carbon fibers and epoxy. I'm sure that you will get different results.
Sure.
Yeah.
Thank you. Thank you so much for the comment.
Just a quick comments about 4R. I know most people in relaxation work like this, curve fitting, but that is not really scientific. In the upcoming 4 documents will include a much more in-depth understanding of the behavior of CFRP subjected to relaxation. Because the relaxation depends on the metrics type, as Brian mentioned. But most cases, including your own study, just curve fitting, okay? Which means you have no idea what happens inside the CFRP material. So advanced concept will come out in 4 documents. With the different matrix properties. So we don't really need to worry about the relaxation component. But you will see more sometime next year, a lot advanced concept in relaxation.
Sure.
Reza and all of our students today.
Thank you.